Cool.
Okay. All
Got
right.
it.
So Neil, are you able to share your screen? Did you test that out?
Yeah, let me give that. I haven't tested it, but I think it's going to be okay. Let me just move the zoom bar before the plot is ruined. Can you see it?
Yes.
All right. Well, hold on. I've lost my cursor. I would like to move this. Oh, 1 second. Let me go out of full screen. Let me move. Whoops. Nope. Didn't want to click that. 1 second. All these zoom bars are preventing me from seeing both you and my slides. So let me just. Okay. Okay. Good. There we go.
Okay. Okay. Let me welcome everyone. Thank you for being here for this. That I'm sure is going to be a very wonderful talk. So Neil is a theoretical nuclear physicist, specializing in many body physics. Right? He's currently a postdoc at MIT. I think he started about a month ago.
Yep.
And before that, he was a postdoc at the Institute for Nuclear Theory at the University of Washington, Seattle, which is where I met. We shared an office at the INT. He did his PhD at the University of Maryland, and I don't know, Neil. Do you want to tell him about what you do outside of physics?
I gave Mwande more than he asked me. Yeah, I grew up. I'm an Army kid, so I grew up in weird places. So even though I'm an American, I grew up in Germany and in Hawaii, which is not very typical. And I also play music. That is the extra that I gave Mwande in case we needed to add a little spice to the intro.
Very good. All right, Neil. Yeah. So anyway, most importantly, Neil was a very good physicist and really communicates with a lot of excitement about his work. And that's because he is always working on exciting stuff. Yeah. So without further ado, I'm gonna leave it. Take it on, Neil. Please take it on.
Forgive me, I'm going to exit full screen one more time because for some reason my cursor keeps vanishing and still it's hard to see what's going on. So just one last time, I promise. I would like to see you guys instead of me. Okay, good. Perfect setup. Good. Okay, good. So, all right. And also, let me just make sure I'm keeping myself. I timed myself once this morning. It took 50 minutes. So this should be 50 minutes long. But if I go over time,
take your time. Yeah.
Okay, sweet. Okay, so basically, I'm gonna give you all 2 lectures on the topic of core collapse supernovae and what it has to do with dilute nuclear matter. Okay, if you have never thought about this topic before, you might wonder what the heck do these 2 things have to do with each other. I hope to communicate to you by the end that both of these are really cool systems and they're intimately linked. So this first lecture is going to be all about core collapse supernovae, and I have made it directed to basically young people who have never thought about this before. So if you're an expert, forgive me, but we're just gonna have some fun, and I'm gonna tell you all about core collapse supernovae today. Next time it's gonna be more technical, dilute nuclear matter. But let's talk about stars. Okay, if you've never thought about stars before, they sort of go through an interesting life cycle. So this talk, we're going to start in the upper left, and then we're going to descend to the lower right. First, I'm going to tell you how stars are born. Then I'm going to tell you how they live, how they support themselves against the force of gravity, and eventually how they die. This is where core collapse supernovae comes into this story. Stars die, some stars at least, die in massive explosion called core collapse supernovae, which has a lot of interesting nuclear physics. And then once we go through that, there's a lot of cool physics there. I'll tell you what this has to do with neutrinos, and then what it has to do with dilute nuclear matter. And I'll leave you on a note. We'll stop on dilute nuclear matter. And if you want to hear about it, you're going to have to come next time. Episode 2. Interesting. Okay, good. So how are stars born? So the short answer is that stars are born in what are called nebulae. Nebulae are basically giant gas clouds in the universe. They look really pretty if you visualize them in the visual spectrum. This one right here is called the Orion Nebula. And basically what they are giant clouds of dust, mostly hydrogen, where clumps of high density form and begin to coalesce under gravity. And those clumps begin to gather and gather and gather. And eventually stars are born by just the action of gravity causing particles to come together. Now, so that's the short answer. That's how stars are born. Dust gathers. This Orion Nebula has a cool story that I wanted to tell you about. So if you look here on the left, you can see my cursor?
Yeah, yes.
Okay, good. On a couple slides later on, you won't be able to. I don't know why, but okay, good. So basically, here's a picture of one section of the night sky as viewed from Florida. We've got Orion in the middle. You can tell it's Orion because he's got the bow and his arm is up. So if you start at Orion's belt, these three stars down here, then Orion's sword sort of goes down from the belts. This circle called M42, there's a shiny bright spot in the middle of Orion's sword called M42, and that, you might think it's a star from Earth because it's a shiny thing in the sky, but actually this right here is the Orion Nebula. It's called the Orion Nebula because it's inside of the Orion constellation. So this is one of many nebulae that are in the galaxy where stars are produced. And one interesting, cool fact about this nebula, besides the fact that it produces stars, is that the ancient Mayan civilization, they're ahead of their time in so many ways, but they just so happen to choose at the center of their mythos that the universe was created in this particular bright spot in the sky. I don't know why they chose this spot, but they chose this spot within the Orion galaxy to be, okay, that right there, that's where the universe began, which is an amazingly lucky guess because this is where stars are formed. You could have chosen a random star, but they chose a good spot. Okay, so short answer, how are stars born? They're born in nebulae. Nebulae look really pretty, so I'm just going to show you a couple pictures, and then we'll start doing some science. They often look strange. So this one, for example, is called the Cat's Paw Nebula. So this orange spot is supposed to be the paw of the cat, and here are the toes. There's other nebula. There's one called the Hand of God, which I didn't include, but it actually looks like a hand holding something. It's almost creepy. An interesting phenomena happens in galactic in giant nebulae. So right here we have what are called magnetic rivers. So by complicated dynamics of charged particles moving through the cosmos, giant magnetic field lines can be created if the conditions are right. And charged particles spiral along magnetic field lines. They're sort of like guidelines for things to move. And these magnetic fields are so big that you can see from Earth or from space-based telescopes magnetic field lines, and these are called magnetic rivers. So nebulae can form really pretty structures. This almost looks like a rift in the matrix to me. I find this almost disturbing. I think it's a cool thing. Okay, so that's how stars are born. Now let's move on to how stars live. The short answer is that stars live by fusion. So basically what happens is in nebulae, stars begin to form by the collection of dust under the force of gravity. You'll see, by the way, throughout this talk that gravity is like this ever-crushing thing that causes cool physics to happen. So it causes initial star formation, and as these hydrogen atoms basically fall in, they speed up. And as a consequence of their heightened motion, they heat up. And once a star gets sufficiently massive and the gravity is strong enough, it gets hot enough to begin the fusion process. And at that point, stars begin to shine. So actually, when stars are first born, they don't shine. They're just clumps of stuff. Once they get massive enough, they begin to shine through the process of fusion. And this is how they keep themselves buoyant against the force of gravity throughout their life. So the basic fusion process that happens inside of stars that keeps them afloat is this process right here. 4 protons, which initially come from hydrogen atoms, the electrons get blasted off by particle motion. 4 protons fuse to make a helium nucleus. This horribly detailed notation just means helium nucleus. I've indicated over here. And byproducts come out. 2 positrons come out of this reaction and 2 neutrinos come out of this reaction. Okay, so I'll say up front, there's a heck of a lot of really complicated nuclear physics hidden in this blob, but at the end of the day, what results is 4 protons turn into a tightly bound helium nucleus and releases a bunch of energy. Okay, so some facts about fusion. You might know this because you're all nuclear physicists, but fusion releases energy. So if you look at the binding energy of helium, a helium nucleus, which you can figure out by shooting it through a magnetic field and seeing how much it bends, the binding energy of this thing is about 28 MeV. That's quite a bit of MeVs. On the other hand, On the other hand, electrons have only a mass of about half an MeV, and neutrinos, we don't really know their mass exactly yet, but experiments are able to bound them, and they're less than a micro EV in mass, okay? So even though you have to make a couple of particles to make this process happen, there is an overwhelming amount of energy left over, and this energy is what keeps stars buoyant. So the net energy is like 27 MeV. That is responsible for helping the star live. I didn't realize everybody would be nuclear physicists, so I guess I don't need to say this. But to put this in context, this is about 1 million times more energetic than chemical reactions. Chemical reactions that happen in your soup are on the order of EV scales, atomic energy level spacings, those are EVs. This is 1 million times more energetic. And this is part of the reason why the sun is such a useful energy source. It runs on nuclear physics and not chemistry. All right, so that's fact one. Fact two, the green blob is complicated, okay? So the manner in which these 4 protons eventually fuse into hydrogen is summarized in this table right here. I won't go through the whole thing, and I don't know if you can see. I apologize if it's too small. But basically what happens is the first thing is that 2 protons come together and make a deuterium and release 1 positron and 1 of these neutrinos. That accounts for these 2 dudes. Then once this deuterium is formed, another proton comes in, joins to the deuterium, it releases a gamma ray, and then it goes through a bunch of steps to eventually form the helium-2+. So this took an entire community, decades to figure out. But now we're reasonably certain that through this chain of reactions, this very simple picture of 4 protons fusing into 1 helium nucleus is what happens and what powers, say, the sun. The last thing I would like to say is that fusion is slow. This is why we can't do it on Earth yet. Successful fusion has happened in certain labs, but not a sustained living fusion reaction. So fusion is slow because it involves the weak interaction. You'll notice protons go in, these are hadrons, this is QCD, but weak interaction particles like the electron and the neutrino come out. And basically, if you zoom in on one aspect of this green blob, what happens is the proton goes through a weak decay, it releases a W+, and then this W+ splits into a positron and a neutrino. And just to give you a flavor of why this is a slow reaction, if you estimate the perturbation of an observable at second order in perturbation theory, this is second order because there's 2 vertices. Well, in quantum mechanics, it looks like this. You've got some energy denominators, which summarize the energy of the intermediate state. And then you have matrix elements of the perturbation upstairs. And basically, this is what matters. So basically, in the denominator, you have the mass of the W square. That's something like 100 GeV squared. But what's on top are nuclear matrix elements, which are on the order of MeV, because nuclear physics happens on the scale of MeV. This is like 10 to the minus 5. You square it, you get 10 to the minus 10. Fusion is really slow. And thank God for that, because if it wasn't, the sun would burn out quickly and we would not be here. Okay, so that's a short summary of how stars live. The short answer is they live through fusion. Okay, so how do they age? I'm slowly trying to get us to core collapse supernovae. Why do they happen? Okay, so what happens is stars, they gather, they heat up, they begin doing fusion, and this fusion becomes a stable reaction which happens for a long time. And the way that stars age is summarized on something called the Hertzsprung-Russell diagram, or HR diagram. So if you look out into the sky and you pluck out a single star, that single star has many properties that can be assigned to it. 2 of them are what's the spectrum of colors coming off of it and how bright is it? The 2 axes on the HR diagram are basically that. The vertical axis is the luminosity in units of the sun's luminosity. So low is low luminosity, not bright. High is high luminosity, quite bright. And as you march to the left, the temperature gets hotter and hotter, the stars get bluer and bluer. And so if you just pluck out, thousands of stars and begin to plot those pairs of numbers, what you find is that patterns emerge. There's a very strong curve in the middle that sweeps across the middle of the temperature luminosity curve, and these have been called main sequence stars. So about 90% of stars are in what is called the main sequence. What accounts for this behavior is just the steady burning of hydrogen into helium. Now, there are outliers that do not lie on the main sequence. There's clusters down here that are low luminosity, but still high temperature. These are called white dwarfs. There's clusters over here, which are the giants. These are large stars, luminous, but not very hot. And then there's supergiants, which are really luminous, but still not very hot. And what this and so as the star ages, basically what happens is it marches along. Oh, I'm sorry. It starts blue and it marches red because it cools off. And this marching happens because it's slowly burning its hydrogen, turning it into helium, and depleting its nuclear fuel. And the sun, for example, is a main sequence star with a mass of 1 solar mass. Now, what's interesting is as the star ages, its ultimate fate, how it dies, if you will, is a sensitive function of its mass. If a star is really massive, it burns through its fuel really fast because the gravity is strong, forcing fusion. If the star starts out not very massive, it actually takes a long time to burn through its fuel. And based on the initial mass, very different qualitative fates occur. Now, I apologize that this figure is kind of small. I kind of wanted to show both of these side by side. But basically, this is a plot. This is an artist rendition, albeit like artists collaborating with physicists, so it's not like totally bogus. But we're looking at as you go up on the vertical axis, we're going higher in mass, and as you go to the right, you're going you're aging the star. So if you start at, say, so all stars start at a protostar. That is when dust gathers and fusion begins. If you're a main sequence star of about a solar mass, like our sun, you go from a protostar to a main sequence solar type star. That means like a star like our sun. It burns through its fuel. And by complicated mechanisms that I won't really get into, the ultimate fate of these stars is to actually grow large. It's a little surprising, but when a star depletes its fuel, it actually gets bigger. So our sun, for example, is going to turn into a red giant, and eventually the giant's going to grow and grow and grow and grow. And eventually it's going to become this diffuse cloud called a planetary nebula. This is, again, a dust cloud. And from that dust comes planets. Now, what's really interesting is if the star's initial mass, if it just so happens to be born in a nebula where its initial mass is between 8 and 20 solar masses roughly, it has a very interesting terminus. So like all stars, it starts off as a protostar, a cloud of dust. It begins to fuse. It turns into a giant, just like our star, our sun will. But then the ultimate fate of such a star is to explode. It goes through what's called a core collapse supernova. And what's left at the center of a core collapse supernova is a newly born neutron star. So I don't know if you knew this, but actually neutron stars are stars which are born from stars. And the way in which they're born is in an explosion. And what I'm going to spend the rest of the talk describing to you is, assuming we have a star that's 8 to 20 solar masses, how the heck could a supernova happen? There's some really interesting and simple physics which leads to this phenomenon. Now, before I go into that, I want to do a quick aside on good science, because the way that so I'll tell you, the HR diagram has guided astronomers, astrophysicists' thoughts since the early 1900s. And the way that it came about, I think, is just beautiful and is a good demonstration of good physics in play. So this may seem unrelated, but like, what's a sphere? A sphere is an object such that when you walk around it, it doesn't change. That's what a sphere is. It's a thing that if you see it on one face and then you move your head, it doesn't change. Not everything is like that. Like a human is not an object such that when you move, it doesn't change. So a sphere is defined by looking at it from many angles. And so it's useful to look at stuff from many angles. So the HR diagram, so H is Hertzsprung, R is Russell. We're going to talk about Russell. This is Russell's data. So basically, we're in 1915. There's these big astronomical tables of data, just books of numbers like you have around you right now, I imagine. I mean, I'm sure there's, anyways, blah, blah, blah. So there's this big table of numbers, and he was trying to make sense of what was going on. And so he just started plotting column against column, seeing no pattern, column against column, seeing no pattern. And then he chose luminosity and color. And what came out was this. And if you drink a beer, maybe two, you'll see a straight line here. And so he published a one-page paper in the Astrophysical Journal and said, look, if you put straight lines right here, these stars, man, they really look like they're just lying on a straight line. And there's just got to be some underlying physics that makes this happen. And there was. And this is what started people to understand how fusion makes stars go. So what I'm hoping to communicate here is that good physics can often be simple and can come from just trying to look at something from many different angles, and then suddenly you've got the right angle and a pattern emerges. This has guided our understanding of stars since the early 1900s.
Sorry, Neil.
Sure.
Could you just say again what are on the axes on this Russell plot?
Yep, yeah. So the axis, so going up the axis, we're going up in luminosity. So photon, how bright is it? And as we go from right to left, we get hotter. So the axes chosen on this particular plot, you'll see it's letters and not numbers. So these are what's called spectral classifications. So when people look at these stars, they basically diffract the colors through a spectrum, and they see particular spectral lines. And if you see a certain set of spectral lines, you call it a K spectrum star. If you see a certain other set of spectral lines, you call it a G spectrum star. And between then and now, what we have understood is that these differing spectrum come from basically the temperature of the star changing and the ability of temperature to excite different atomic transitions. So while in the original data, it's plotted as spectral index, this really can be translated into temperature.
Thanks.
Cool. Yep. Okay, so we know how stars are born. We know how they support themselves. How do they age? Okay, well, the first step, as I just told you, is hydrogen is fused into helium. That's a really energetic reaction. But at a certain point, you're going to run out of hydrogen. And indeed, stars do. And what happens once that happens is, well, you got some helium sitting around and you've got gravity pushing the heck out of them. Helium is able to undergo something called the triple alpha process. You probably all know this because you're nuclear physicists, but another name for a helium nucleus is an alpha particle. And just like how you can take 4 protons and fuse them into a helium, you can take 3 helium and fuse them into a carbon nucleus. It's a similar process. And just like how inside of the green blob, there was a lot of complicated nuclear physics hiding, the triple alpha process is really complicated. It's sort of summarized in this plot right here. Basically, two helium nuclei, 2 alpha particles join to form an excited state beryllium nucleus emitting a gamma photon. And then a 3rd alpha particle joins this beryllium and it comes carbon. This is simplified compared to reality, but the end result is helium gets fused into carbon. And then once helium is depleted, carbon fuses into oxygen, oxygen becomes silicon, silicon becomes iron, but then everything stops at iron. And this is really interesting and is what ultimately causes the core to collapse. So to sort of explain what's going on here, again, I bet these plots are real small, forgive me. So what we're looking at here is the binding energy of nuclei as pulled from the Nuclear Data Science Center as a function of number of nucleons in the nucleus. So right here, we start at hydrogen, deuterium, helium-3, triton. Maybe you'll see helium-4 is really, really bound. There's a big spike at helium-4. This is why helium is what results from fusion in the sun. It's really bound. And then, okay, after helium, we go to lithium. Lithium, it might not be visible, but there's a spike at carbon. This is why helium goes to carbon. You'll notice, again, there's a spike at oxygen in binding energy. This is why carbon turns into oxygen. Silicon is a tiny little peak in here, but you can't really see it. But this is why silicon happens next. But now, as you'll notice, as the nuclei gets bigger, these curves become much more smooth and eventually drop off. There's a maximally bound nucleus, which is iron. Therefore, what that means is as you begin to crush nucleons and they fuse into bigger and bigger nuclei, this process will terminate at iron. There's nothing more bound than iron, so you can't fuse beyond iron. And so as a result of that, the main mechanism for the star supporting itself just stops at iron, and it develops an iron core, which grows and grows over time. Basically, iron is a depleted nuclear fuel. And at this point, the star's in trouble. It starts to run out of juice to support itself. And once the iron core gets of sufficient size, called the Chandrasekhar mass, it collapses and explodes. So that's how stars age. I'll go into detail on the collapse of the iron core. But basically, the main message here is stars age by making bigger and bigger nuclei, and they run out of fuel once you reach iron. Okay, now we're going to go into core collapse. How does that happen? First, let me give you the executive summary before we get into the details. There's a lot of numbers. So as I just told you, the core where iron is formed, it ceases fusing. What that means is that the iron core is actually quite cold compared to the rest of the environment. It's cold because it's not undergoing fusion, and fusion is the source of heat. In fact, what keeps the core buoyant is electron degeneracy pressure. We'll see that in a slide. So basically, this thing is not kept up by thermal excitations. It's kept up by quantum mechanics and electrons being fermions and not wanting to occupy the same space. Now, what's interesting, this takes a lot of research to figure this out, but the density of the iron core, this isn't your mother's iron, my friends. This is very, very dense iron. This is 10 to the 8 grams per centimeter cubed. Compare that to terrestrial iron that you might pick up. It's 7.8 grams per centimeter cubed. It's about 10 million times more dense. So this is iron crushed beyond crystals, really, really dense. What eventually causes it to collapse, as usual, is gravity. Gravity is like this insurmountable force that just crushes everything, but which makes cool physics happen. Okay, so what's really annoying is that my cursor won't show on this slide. So I hope you'll forgive me. I'm just gonna exit full screen and try to get rid of as many things as possible. I don't want to see anything. Good. Okay, so I'm doing this so that you can see my cursor. So I'm gonna tell you, if you already know this, forgive me, but you get really cool physics out of simple assumptions, just like the HR diagram. Really simple stuff makes good physics. So how does degeneracy pressure happen? Okay, here's how degeneracy pressure happens. If you solve particle in the box quantum mechanics, H psi equals E psi, with a box of length L, what you find, as you probably know, is that the energies look like P squared over 2m, where the energies are quantized in units of 2 pi over L, where L is the length of the box. So, you put one, and let's think about fermions, okay? So you put one fermion in a box, it has a little bit of momentum, a little bit of energy. You put the next fermion in a box. If you keep putting them in, eventually you're going to stack up into higher and higher energy levels and actually make a quite energetic box of particles. And this comes solely from the fact that fermions don't occupy the same space, same state. You can visualize what is happening by plotting the axes px, py, pz, where those are the components of the quantized momenta, which you fill one by one. So the first, the picture's small, I know, forgive me. So the first fermion that goes in, no momentum. The next energy level are 1 unit of momentum in any direction. So you can fill 1 unit this way, 1 unit in the y direction, 1 unit in the z direction, and the same in the negatives. Eventually, you're going to fill up higher and higher states and make a spherical shape in momentum space. And the spherical shape represents the states filled by the many fermions which fill the box. And so you can figure out the energy of such a box of fermions in the following way. Forgive me, this is kind of mathy, but this is important for what's to come. So suppose I know I've got 10,000 fermions, I'm going to put them in the box. Okay, I can deduce the highest momentum state filled by, say, 1,000 fermions through the following logic. Okay, well, the number of fermions, I get to choose that by hand. What's that? Well, it's 2s plus 1. Let's think electrons, because we're going to ultimately talk about electron degeneracy. Electron's a spin 1/2 particle, so I can put a spin up in the lowest momentum state, a spin down in the lowest momentum state. So that's this 2s plus 1. That's a factor of 2. And then I just sum 1 unit for every occupied state. Okay, so how do I sum over occupied states? The trick in how to do this is to notice that the spacing between energy levels in momentum space is 2 pi over L. The reason for that is the momenta are quantized in units of 2 pi over L. So if I go from nx equals 1 to nx equals 2, the amount of momentum increase is 2 pi over L. So you can use that. That's a super crucial fact and is really useful. So going from this first equality to the second equality, I'm just multiplying and dividing by d cubed p. By dp, I mean 2 pi over L. So I have a d cubed p inside, and I can insert that at the cost of getting a volume over 2 pi cubed outside. Now, what's really cool is if you take the volume of the box very large, this d cubed p converges to a legitimate integration measure. This becomes an infinitesimal quantity. And what that allows you in a large box is to convert the sum into an integral. What that means is that the number of fermions in the box can be related to the highest filled momentum, which I'll call PF, it's often called the Fermi momentum, through the following formula. You integrate momenta up to P Fermi, and there you go. Solving this integral, it's not hard. You can relate the highest filled momentum level to the number of particles for volume, and that's what you get. The highest filled momentum, the Fermi momentum, is basically the number density to the 1/3 power times a numerical factor. So immediately you can read it off that if you make a system denser, the fermions fight you harder. Their highest momentum increases. Forgive me if you already know this. So you can use this to compute the energy of a bunch of fermions in a box. You go through the same construction. What's the energy? I get a 2s plus 1 because every state is doubly filled. And then I just sum up all the energies. Well, we know because we solved the single particle problem that the energy levels are p squared over 2m. So in the large volume limit, the energy of a bunch of particles in a fermions in a box looks like this. You integrate up to the highest filled energy level, p Fermi, and you've got the energy appearing. You do this integral, and what you find is that the energy density goes like p Fermi to the 5th power divided by the mass of the particle. Now from this, so again, you'll notice p Fermi, it gets bigger with increasing density. So the total energy in a box goes up with increasing density. From this, you can figure out the pressure exerted by fermions in the box. And that's where I'm really headed here is what is degeneracy pressure? You combine the simple quantum mechanics that I just showed you with thermodynamics. Well, the pressure of a gas is you take the derivative of the energy with respect to the volume while holding n fixed, and then you take a negative sign. Now, there's a chain rule here because the energy depends on p Fermi, but p Fermi depends on the volume. So there's a little bit of algebra to do here. But at the end of the day, what you find is that the degeneracy pressure of a bunch of fermions is p Fermi to the 5 divided by m, again, times a numerical factor. I would say that this is a whoa moment, my friends. From simple considerations, simple quantum mechanics, non-interacting particles, combining it with thermodynamics, a new concept emerges, degeneracy pressure. Again, simple physics can take you far. Okay, so this is how the iron core stays afloat. The electrons exert this degeneracy pressure, which we just derived. Now, I think if I go, how do I go to the next slide? Irritating. All right, I'm gonna do this. Oh, no. My cursor does show on this one, so we'll do this. Okay, so we're getting to how do stars die? How do they explode? Well, at first, the iron core, so right now we're just thinking about the iron core, forget about everything else, is supported by electrons. We just derived that the Fermi momentum is an important quantity. It's like the cube root of the number density, and the degeneracy pressure is like the 5th power of that divided by the mass. So you can deduce some interesting qualitative conclusions from these simple considerations. First off, inside of an iron nucleus, iron 56, say, the nucleus is 23 protons, 23 neutrons, and 23 electrons surrounding it. That means if you take a bunch of iron atoms and squish it, whatever that matter does, the density of electrons, protons, and neutrons are identical because the ingredients inside of it have identical numbers of protons, neutrons, and electrons. That means that the electrons exert more degeneracy pressure. So the p Fermi for all the particles is the same because they have the same number density because there's the same number of everything, but the degeneracy pressure goes like 1 over the mass. So if your mass is small, you get a lot of pressure. So because the ratio of masses between protons and electrons is like 2,000, that means that the electrons exert 2,000 times more pressure than protons. This is why I have been asserting that the electrons and not the nucleons are what keeps the iron core afloat. Another thing which you can find with a supplemental piece of information is that the electrons within this system are in fact relativistic. They don't move slow, they move fast. Now, this is kind of not trivial to see. It requires you to know what is the density of the iron core, and that is difficult to figure out. But there are people who think about this quite hard. For example, this group right here, they do simulations of star formation with very detailed models of microscopic physics. And I'm just showing you one plot. So what we're looking at is, all right, we're inside of a main sequence star, starting off between 8 and 20 solar masses. And we're starting at the center of the star. And as we march to the left, we're going to the periphery. Now you'll notice that this axis is mass. The mass is like the radius. So this is the amount of mass enclosed as you go to the left. So at the center of the star, 0 mass is enclosed at the center. As you march out in radius, more and more of the star is enclosed. So you can think of this x-axis as a stand-in for the radius. On the top axis, we have the density of the stuff in units of grams per centimeter cubed, log base 10. So I just want to draw your attention to this band called 3. This is the iron core. And if you look, it basically goes from 10 to the 10 grams per centimeter cubed to 10 to the 7.5 grams per centimeter cubed. Okay, I'm saying 8 is somewhere in the middle, and that's where this figure 8 comes from. It's a rough figure. But if you say, okay, I'm going to put electrons in an environment that has a density of 10 to the 8 grams per centimeter cubed and undo this equation, what you find is that P Fermi for the electron is about 5 times its mass. So these electrons are relativistic. They're not ultra relativistic. It's not like 1,000 times the electron mass, but they're indeed relativistic. And what I'm about to show you is that the fact that the electrons are relativistic is what makes the core collapse. That one fact. Okay, okay, again, I have to go out because you can't see my cursor. So let me introduce you to a word, the Chandrasekhar limit. The Chandrasekhar limit is the limiting mass after which the core collapses and causes a supernova. Here's how you derive the Chandrasekhar limit. Here's the game. You consider a mass of stuff of equal numbers of electrons, protons, and neutrons, because that's what the core is, of a given radius r, or mass m, radius r. Now, what we just found is that electrons, because of their small mass, provide most of the pressure and most of the kinetic energy. On the other hand, the nucleons, which are sitting there, which have about 2,000 times more mass, account for most of the gravitational energy. So what we're going to do is we're going to estimate what's the energy of such a chunk of matter. And we're going to make the simplifying assumption that all of the kinetic energy comes from the electrons and all of the gravitational energy comes from the neutrons, from the nucleons. And we're also going to assume that the mass is of uniform density. All of these assumptions are false, but they are not terribly false, and they can give you a rough picture of what's going on. So the energy has 2 parts. There's the kinetic energy and there's the potential energy. The kinetic energy we just learned how to do. I integrate up to P Fermi. I've got to put in a relativistic dispersion relation because the electrons are relativistic. And I pick up this factor of volume out front because of the large volume limit. So if you don't want to deal with the square root, you can just expand this object. And the total kinetic energy inside the system is an integral up to P Fermi of P cubed mass squared times P yada yada. We're just going to keep these first 2 terms because the electrons are not terribly relativistic. Now, I'm not going to show you the result of this integral. It's more details than we need, but you can do this integral. Now, the gravitational potential energy is simple to derive. It's a fun exercise too. It's -3/5 g Newton, the total mass of the star squared divided by the radius of the star. So what we're going to do is we're going to say, suppose that I've got a chunk of matter of fixed mass m. What is the equilibrium radius of such an object? Now, so we're going to write this energy in function as a function of r, take a derivative and set it to 0. And from out of that comes the Chandrasekhar limit. Now, the potential energy is already written in a nice form. I've got a fixed mass. I'm going to hold that fixed. The radius is what I'm going to vary. The kinetic energy right now is annoying because it's written in terms of P Fermi. But you can rewrite the kinetic energy in terms of the total mass and the radius because P Fermi is related to the number of particles, which is related to the mass, and the volume of the system, which is related to the radius. I'm not going to do that, but T can be converted into a function of a fixed m and a variable r. And what happens, again, you can't see my cursor. How annoying. Okay, so I'm skipping these steps, but the result is that the energy as a function of r has 3 terms. There's 2 terms which go like 1 over r, and there's 1 term which is linear in r. And these coefficients A, B, and C are kind of ugly. They're right here, okay? So A, this comes from, the first term in the calculation of the energy, the kinetic energy. B comes from the gravitational mass term. C is the subleading correction to the kinetic energy. Now, let's think about this, okay? So first off, C is a positive number. C is a positive number. So that means if I plot energy versus R, at large R, we're going to have a straight line going up. Now, at small r, this term's going to dominate because it diverges, and you're going to have 2 qualitatively different behaviors depending on if A is greater than B or if A is less than B. So if A minus B is greater than 0, then this curve is going to turn upwards at small r. And if it's less than 0, it's going to turn downwards at small r. So you'll see then that if A minus B is positive, we will have a solution. We will have an equilibrium radius that the star will settle at. However, if A minus B is negative, I will not have a solution, and there will be no equilibrium radius. So the point where A equals B is the definition of the Chandrasekhar limit. It's the limit where you cannot minimize the energy and the star has no stable configuration. And if you just set A equals B and solve for capital M, the mass of the star, what you will deduce is that the Chandrasekhar limit is 1.72 times the solar mass. Okay, so once that iron core becomes 1.72 times the solar mass, it's going to collapse. It's going to collapse because gravity, which is the B term, beats degeneracy pressure, which is the A term. Now, one thing I'll tell you is that this number 1.72 is not the number that you'll see if you open up your textbook. The more correct Chandrasekhar mass limit is 1.4 solar masses. The reason we're getting 1.7 and not 1.4 is because we made some assumptions which were not true. We assumed constant density, and we only kept the first two terms in the relativistic expansion. If you do a more detailed calculation, which is harder to do, you will go from 1.7 to 1.4. But the qualitative physics is the same. Basically, gravity wins over degeneracy pressure at roughly 1.5 solar masses. Okay, so again, check this out, guys. This is free fermions, thermodynamics, and Newtonian gravity. Combine these three things, and you get that stars explode. Very interesting physics can come from very simple assumptions. Or not very simple. You can get good, interesting physics if you just open your eyes. Not that I can do, not that I can do this myself. I just want to point out that really interesting stuff is coming out of this. Let me tell you another cool piece of history. So here's the original paper by Chandrasekhar where he derived this limit. It's 2 pages first off. Think about that, man. A 2-page paper. I want to write a 2-page paper. That sounds lovely. If you do a word count on this paper, there are less than 500 words in this entire paper. Okay, there are more words on the back of your cereal box, my friends, than there are in this paper. So again, simple stuff. You can get good physics out of simple stuff. Okay, cool beans. So we're basically getting to the end of the star's life. If the iron core gets beyond the Chandrasekhar mass, it collapses because gravity wins, and then an explosion happens. Now, interesting things happen during the collapse. First off, it's a runaway reaction. It's a runaway reaction for several reasons. First off, as this core collapses, basically you have a bunch of charged particles zooming towards the center. If you accelerate a charged particle, they emit light. What this does is the accelerating electrons emit gamma rays. These gamma rays hit the iron nuclei and begin to blast them apart into smaller constituents. This sucks up energy from the system and causes the collapse to happen faster. Furthermore, electrons, your main source of pressure, are lost during the collapse. The reason they're lost is because electrons run into protons through a reverse beta decay process and produce neutrons and neutrinos. So you begin to bleed your system of the one thing supporting the system that speeds up the collapse too. Finally, neutrinos, which come out of this reverse beta decay process, and there's actually a whole bunch of reactions which can produce copious neutrinos. These guys are electrically neutral particles that only interact through the weak interaction. They just escape out of the center and bleed the system of more energy. These three factors cause the core collapse to happen very quickly. It happens, I forget the figure, but it's on the order of seconds. The whole thing collapses. Now, one thing I'll say before I move on is because of this absorption of electrons on protons, what results is a neutron-rich medium. And this is a part of the reason why what's left after at the center of a core collapse supernova is a neutron star. It's a neutron star because the protons are destroyed by the electrons. That's one part of how it becomes neutron-rich. Now, okay, so the dynamics of the core collapse is extremely complicated, and so I'm just going to have to wave my hands. Forgive me. So basically what happens is the iron core collapses because gravity wins. That matter becomes extremely dense. At a certain point, the neutron degeneracy pressure and nuclear forces prevent it from collapsing too far, and it bounces, and the bouncing core slams into matter and initiates the explosion. That basically results in what's called a proto-neutron star at the center. That's a hot neutron-rich star, which eventually becomes a cold neutron star. And it causes the matter to zoom out a little bit. Then what happens, this comes out of a bunch of years of work of simulations, is actually that first shock is stalled. There's not enough energy from the initial kinetic impact to make the supernova actually blow off. What makes the supernova blow up is the enormous flux of neutrinos, which slams into that stalled shock and pushes it outwards. And so I'm trying to sort of depict that here. So basically, we have a proto-neutron star. That's the middle. That's the old iron core, which has collapsed. Many, many neutrinos are coming out of this. And because this matter is so dense, they're at first in thermal equilibrium with this stuff. So they're just bouncing along through the proto-neutron star, tracking its thermodynamic information as it goes because it's in equilibrium. Simply because the matter is so dense. At a certain point, however, the matter becomes dilute, and the neutrinos are able to exit equilibrium with the dense nuclear matter. This is where neutrinos decouple from the matter, and this layer, this blue layer, is called the neutrinosphere. And the neutrinosphere will be the topic of my next talk. What's important about it is that one, neutrinos decouple from the matter here, and two, and most importantly, the neutrinosphere determines the spectrum of energy of neutrinos coming out, and in this way influence heavily the outcome of a supernova. If somehow the neutrinosphere is able to suck up all the neutrinos' energy, then the neutrinos won't be able to revive the stalled shock. So the neutrinosphere is a very important system, which we'll talk about soon. Before we get there, let's take a break and watch a movie, shall we? So what this is a state-of-the-art simulation by NASA of a main sequence star of mass between 8 and 20 solar masses undergoing a core collapse supernova. So basically, you'll see it begin to get bright. This is because of the initial collapse, the radiation resulting. Boom, this first wave of things is neutrinos. That second wave of stuff is the matter which was slammed into by the neutrinos and which comes afterwards. Oh, shoot. Sorry. So one more time, now that you know what's coming, the core is collapsing, accelerating charges. Many gamma rays come out of that. Now the neutrinos are going to come. They come out of the matter first because they're only doing weak interactions and they have less mass than the rest of the matter. So they escape first. And in fact, we can detect them on Earth. And then afterwards, the matter which was struck by the neutrinos come on. Okay. Whew, a lot of details, guys. Forgive me. All right. Last topic. I'm going to introduce the neutrinosphere to you. It's an extremely interesting system, which is important for the dynamics of core collapse supernovae. And then we'll wrap it up. And then next time will be all about neutrinosphere and the cool nuclear physics that happens in the neutrinosphere. But here, to give you an executive summary of what is the neutrinosphere. What is it? Well, it's a gas of about 90% neutrons and 10% protons. It's neutron rich because of the reverse beta decay that we talked about 2 slides ago. So it's a gas of nucleons. It's low density on the scale of nuclei. Okay, so it's about 3% the density of nuclei, and its temperature is about 5 MeV. So I would say, on the scale of like Rick collisions and things like that, it's a kind of a dilute system that's not that hot. Nevertheless, it is a strongly interacting gas, and I'll justify this assertion, and this will be the last thing that we go through today. So sussing out these 2 properties, again, takes experts a long time to figure out. But just to show you, so over here, I've got some results of a supernova simulation by David Radice and his collaborators. And what they do is, it's great work. They simulate a core collapse supernova and they just track the neutrinos. And whenever the neutrino goes out of equilibrium with the matter, they put it in a bin and they keep track at what density and at what temperature that happens. Okay, so this first plot is density, this first plot is temperature. And if you untangle this data, what you find is the following. So on this horizontal axis, we have nuclear density in terms of nuclear density in percent. So the assertion of 3% nuclear density comes from these simulations. So they decouple at about 0 to 3% nuclear density, and they decouple at temperatures between about 2 and 9 MeV. So this is how we know the thermodynamic conditions of the neutrinosphere, through state-of-the-art simulations. Okay, so last thing, it's a strongly, if I think this is very interesting. Why is this gas strongly interacting? It's dilute and it's not very hot. What the heck is going on? Okay, the short answer is because nuclear physics is really strong. So to explain to you why this gas is strongly interacting, let me just spend 2 seconds on cross sections. I didn't realize we would all be experts on this. But okay. So what's a cross section? Simple. Here's what a cross section is. I've got some beam of particles. They're coming in. This beam has a certain flux, a certain number of particles crossing a given area per unit time. Say that I've got a beam of light, and I know 1,000 photons are coming through this given area every second, something like that. All right, if I put some target up in there and I have a detector nearby, then some fraction of these photons are going to scatter, and I can collect over here the scattered particles. And if I have an incident 1,000 photons per area per this beam area per time, and I collect, say, 10 photons per unit time, then I can assign an area to what is sitting there. The cross section is the amount of area which accounts for the observed scattering. Okay, so it's like it's how much of a thing you would have to put there to account for, say, 10 out of 1,000 particle scattering, 100 out of 1,000 particle scattering. Good, you guys know this. Now, why am I bringing up cross sections? Well, at low energies, so cross sections, as you guys know, are complicated functions of energy and angle and stuff like this. But at really low energies, they go to a constant for non-relativistic systems, like low energy nucleons. And what this cross section converges to is 4 pi a squared, where a is called the scattering length. So you can think of low energy scattering as the scattering of a bunch of balls of radius a, give or take. Okay, you guys know this from quantum mechanics. Here's why this is important. If you look at this gas of nucleons in the neutrinosphere at 3% nuclear density, the reason why it's strongly interacting is because the nucleon-nucleon scattering length is negative 18.9 Fermi. Don't worry about the negative, okay? Cross sections are a squared anyway. It's just a convention. Roughly speaking, what this means is that when a neutron runs into a neutron, to each other, they look like balls of radius 18.9 Fermi. On the other hand, the interparticle spacing of particles in a gas at 3 times nuclear density is about 5 Fermi. So these particles are way bigger to each other than they are spaced out. If you place yourself in the gas and you ask, what does this gas look like to neutrons? It looks like this. They look like a bunch of overlapping balls, which are never free from each other. This is why the neutrinosphere is strongly interacting, and this is why you can get rich physics out of such a dilute system. The scattering length is enormous. Okay, so that's what I wanted to conclude with. Next time, so basically when a neutrino passes through the neutrinosphere, one, it's an important system because the neutrinosphere is where the spectrum of neutrinos is set. On the other hand, it's a challenging system to understand because when a neutrino scatters off this gas, it never scatters off one neutron at a time. It scatters off many neutrons at a time. So if you want to understand what's going on, you have to solve the many-body problem. And that's what we'll do next time. So with that, I will thank you for your attention. And if you all have any questions, I'm happy to talk.
Thank you for that very nice talk, Neill. So now I'm going to open it up to the floor for some questions. Forrest?
Yeah, I just wanted to ask, can you go back to the Chandrasekhar car, limit, and where you derive the energies? Yeah, this one. So you say A is equal to B is a Chandrasekhar limit. I don't quite follow how setting, or I don't quite follow how when A is equal to B, you have the Chandrasekhar limit because you have an energy as a function of R. So how would that term that's proportional to 1 over R, how would that being 0 give you this thing?
Gotcha. Yeah. So so that's a good question. So A equals B is an annoying limiting case. What is true, however, is that when I'm gonna exit so you can see my cursor. When A minus B is positive, you certainly have an equilibrium solution to this equation. Would you agree with that?
Yeah.
Okay. Good. Okay. So at the point A equals B, the method breaks down. You have no equilibrium solution.
Okay.
The reason for that is when A equals B, E is just C times R. And if you try to minimize this thing, you'll see that you can't. There is no minimum. It's just a straight line that goes up forever. So some qualitative change of behavior occurs at the point when A equals B.
Oh, okay. Okay, I think I see. Yeah, yeah. It has to do with the minimum of E equals E of R.
Exactly. Yeah. So A equals B is the point where the minimization game breaks down.
Yes. Okay, that makes sense. Okay, cool. Thanks.
Yeah, to go 1 or 2 slides forward, or maybe 3.
Okay.
Yes, this one. So you said that you had a proto-neutron star in thermal equilibrium, and that eventually you would have neutrinos that exited that equilibrium. But before that, you said that the star seemingly also went out of equilibrium. How does that happen?
Yeah, that's fair. I should relax my words a little bit. So as the protoneutron, first off, if I said it was in equilibrium, that was incorrect. So the protoneutron star, when it first forms, is cooling off. It's dynamic. It is certainly not in a stationary state. So fact 1. 2, however, as a neutrino propagates from the center throughout it, it is in local equilibrium with this thing. So you'll have some temperature profile, which is dynamically changing in time. However, for a given little bit of its path, the neutrino will take on the characteristics of a small little box of the protoneutron star that it's in. So I would say that the most correct thing is that as the neutrino diffuses out of the system, it roughly tracks the behavior of the system, but nothing is in true equilibrium.
Okay. Yeah.
Yeah, I should relax my words a little bit there.
I had another question as well, just
Sure.
on the scattering length and the spacing of the neutrons. It's very interesting to me that the actual scattering length is much larger, or not much larger, but larger than the interatomic spacing. Does that, do you think, create bound states, or does it do precisely the opposite and just cause them to constantly jostle against each other?
Right. Okay, so this isn't obvious, but it's a fact that there's no bound state of 2 neutrons. However, there is a bound state of protons and neutrons, and that's called deuterium. So in this gas of 90% neutrons, 10% protons, there does emerge a certain fraction of deuterium as well. I glazed over that detail because it was a complication, but some of them do pair up and make deuterium. So really, this is a gas of protons, neutrons, and a little bit of deuterium, but I glazed over that detail.
Okay.
Nevertheless, but what's interesting is, so the neutron scattering length is enormous. Also, the proton-neutron scattering length is enormous. The proton-proton scattering length, all the scattering lengths are enormous. So no matter what 2 species you choose, they're going to look like a bunch of overlapping particles. It's kind of crazy.
Okay. Yeah.
Yep.
Good. Any more questions? Even from the people online?
William said that I'm a fan of abstract expressionism because my title slide was a Rothko. Good eye, William.
Okay, well, I have a question now. So you start off with an iron kind of core that's much denser than ordinary iron, right?
Yep.
And then somehow in that core collapse, you end up with nuclear matter that's less dense than ordinary matter. Is that what I'm getting?
No, definitely not. The result
Okay.
after collapse, it's tremendously more dense than ordinary matter.
Oh, okay. But okay, I see. And so the fact that it's dilute, what sense is it? What does the density? How does it compare to like say saturation density?
Okay, yeah. Let me clarify that point.
Yeah.
So this stuff, this protoneutron star, is beyond the density of an iron nucleus or of a lead nucleus, which is what defines saturation density. It's only once you, so this is mad dense, mad dense, mad dense. Okay, now as you get to the periphery, this is the stuff which is 3% nuclear density. So let me say this actually. So ordinary matter is a nucleus surrounded by electrons. So even though in ordinary matter, you have pockets of high density where the nuclei are, ordinary matter is way less dense than a nucleus because it's mostly empty space. So this stuff is pure, it's nuclear matter of 3% the density of a nucleus, but this is still way more dense than terrestrial matter because it's not of atomic composition. It doesn't have that big empty space of an atom. Does that make sense?
Yeah, absolutely.
And then as you get out, less dense. Yeah, anyways.
Okay. And you said it's 10% protons and 90% neutrons, right?
Give or take. Yeah, those are rough figures.
Okay, and what? The neutrinos, I guess, don't even factor for this. They're so light. Is that what's happening?
I'm sorry, I couldn't hear that. Say that one more time.
Neutrinos, what do you call it? The neutrinosphere.
Right.
Where are the neutrinos?
I see. Right. So, okay, good question. So this matter is, if you look at a box of it, it's going to have protons, neutrons in the fraction that I said. The neutrinos come into play because they pass through it. So there isn't a stationary density of neutrinos that just sits in here. Because they only engage in the weak interaction, the neutrinos will pass through this matter, will scatter off of it, and will continue on their way.
Okay, very good.
So then what is the difference between the neutrinosphere and the mass that comes off it?
What is the difference between
what is the boundary between the neutrinosphere and what's awkward?
So there isn't really a sharp line, which is the edge of the neutrinosphere. The neutrinosphere is a region where decoupling begins, and there's a continuous variation in density between the neutrinosphere and vacuum, which is what's beyond. So I'm not sure if that answers your question. So the neutrinosphere is a fuzzily defined region as the region where neutrinos begin to decouple, and it has the temperature and density ranges, which I quoted. Does that answer the question? Or was the question what comes after?
No, the question was basically how do you define the area of the neutrinosphere?
Yeah, the short answer is it is a fuzzily defined concept. Okay. It's fuzzily defined, but it's but it's still useful. There is definitely a region where very quickly the matter drops in density, where neutrinos go from scattering a lot to scattering a little bit. Now, the very edge of where that happens is there's no clean edge to it, but it's still a well-defined region.
Okay, so now that folks have had some time to think a little bit, questions? Any more questions from the floor?
Cool. Thanks for coming, guys. I really appreciate it. I know it's like 5 p.m. or so over there. It must be time to go home and relax.
That's it.
Almost.
Wait, what time is it?
It's about 3.
Okay. I thought you. Okay, my bad.
No, not too bad. Yeah. And so the online people, any more questions? Okay. I have one more.
Okay.
Yeah. So the neutrinos there inside this proton neutron star is I mean, they act in a way that I wouldn't expect them to, right? I imagine neutrinos to be these things with such a small interaction cross section with whatever they're interacting with. And
Yeah.
now you claim they're in some kind of equilibrium or semi-equilibrium with the medium, with the
Correct.
what's going on there?
Yeah, so the reason for that is just the extremely high densities in there. So within we don't know exactly what densities are probed, but 3 times nuclear density is not a crazy density. Like, that's within the realm of possibility that at the center of a protoneutron star could be between 2 and 3 times nuclear density. And if you just calculate, okay, neutrino scattering off of a neutron in vacuum, you get a cross section. If you calculate the mean free path of a neutrino given that cross section, you will see that at 3 times nuclear density, it scatters a lot. So what is unexpected, what causes this difference between expectation and reality is the crazy high density inside of this thing.
Okay. And what's the density again of this protoneutron star?
It could be as high as 2 to 3 times nuclear density in the center, and then as you go to the periphery, it decreases in density. And I don't know off the top of my head really the rate of that decrease, but it can get to multiple times nuclear density inside.
I'll ask a follow-up related to the neutrinos being so weak. I mean, just not having a small cross section. You said that this neutrinosphere gets like a big boost from the neutrinos that pass through. But also, like, I mean, because the cross section is so small, is that just because there's so many and they have a lot of energy that they get this boost, or?